like once x over one. If it will like it symbols, then we have it's going one, right? What fundamentally is this factor out of? Please tell. What should you think it's a vector? Right? X transpose. We'll call this vector, right? Let's go. Right? Vector V versus X comma Y. Transpose of that is going to be vertical column vector, right?
Okay.
You multiply you multiply column vector by greater vector, right? Because x1, y1, x2, column vector, or row column. You get this thing. What do you call this? In the word for it, it's called the inner product. I think it's dot products as well. Yeah, I'm not going to go for inner dot products. So I want to do like short minute explanation of how these things, okay? Now, you know the confidence? Oh, wait, whatever you know before. No. Okay, sure. So, idea is that you can use confidence over Z, right? Which is literally just your additive component, minus the imaginary component. So, like, next one plus J, you just plus over J, right? This is synonymous with just putting them on the back, right? The x1, x2. And the same way you can do an in product with this vector, you can do an in product operation if instead you just like you multiply the number.
I try to set up the Zoom, try to do recording, so I haven't quite do it really well. But anyway, let's do some quick start, even though there's some transcription. And let me do the full. Anyway, we'll do that. Why this option here? Transcript stopped it. Then what's that? Anyway. Anyway, so hi. And I'm Eric Chang. I'm not quite sure how many of you know about me. And I joined the Disucss last year. My expertise mainly on power electric vehicle energy system. So the course mainly to show you about the electric vehicles and aspect is focused on machine, motor, generator. And tell me more about what you understand about the motion system or electrical machine. Have you any one of you have learned anything about motors? What's the background for motor? What do you have more about your background?
I know motors are cars. Motors are a staple electrical appliance. Every day.
I know that electrical motors are powered using magnetic currents. From electrical conversion to magnetic, conversion to mechanical power, basically what that means. And have you ever controlled? Yeah, you want to comment?
I was just gonna say,
the extent that I imagine it would work is you have like a magnetic dipole as a the axle, and then you have a bunch of like inductors that kind of rotate, apply a torque to the axle. That's how they turn.
Very good. So you do have a really good background on motors. But have you really operate or construct or make a motor? Have you done anything about motor really to control or develop your own?
I use like a commercial motor controller or electric speed controller to control brush and brushless motor, but I don't know how it works. I can see you do it.
Yeah.
Maybe we'll do similar. You know, there's a system like a black box with a high current, and then you have output. You don't really just care the internal configuration. But in this lecture, we're going to show you some basic principle of motor so that you know what it is. And then for more advanced topic, then you need to go to the next level, possibly in year 4, maybe in year 5 master. I'll show you more details. But this lecture will show you all the basic principle of electrical machine. So when we say machine, we don't say motor. Why is that? Because motor is for motoring. But somehow we can also have generation. Motion become electrical power. Generator, like the grid power. Like most of generator, wind power is one of the generator we also work on. We also have application, how we use the motor, for example, like electric vehicles, one of the important application. Another important application would be robot. I've been telling many students say, if you want to involve in the robotic system in the future, probably you understand how to move, how to control the motor. One of the big things I can see that today we got 8% of vehicles in the US are electric vehicle. I think in the next 10 years will be 40%. In the next 20 years will be 80% of each vehicle. That's to say you got a lot of the job opportunity of research in this area. You convert all the vehicles into electric, so they all operate by motors. In a typical vehicle, beside the key motor, the main motor, actually there's more than 50 motors in the vehicle. Some of the vehicles have more than 100 motors. They control various movement. So that's why motion control in a vehicle is so important. This way you can see that in robot. You see a robot, you're not only looking on the control, balancing, doing this kind of the job, but also many of the motion control. We have something like rotation motor, we've got a linear motor. Now then you also have 3D motor to move in multiple. So that's why motor control is getting important. How to construct motor, understand motor is also important. You see in another application like mobility. Mobility is something moving, that including vehicle, boat, vessel, aircraft system, space vehicle. They all involve electric motion control. Like aircraft system, maybe some of you involved in aerospace system. The aerospace system, today we convert all the aircraft gradually to work more electric or all electric. We don't like to use jet engine, the pollution, energy wasting. We tend to use electric motor drive. So that's coming in the next 10 to 20 years. So that's why you can see that the electrical machine is getting more important. So that's why I develop these courses. So to have a much more and it's important. I think you all need to understand more about it. Anyway. So first question we like to all ask of you will be machine. I think you understand what it is. And then we see how about history. Which one developed the first motor? You can check the website, you can be able to find a number of the inventor, right? Later on we discuss the bit. What we discussed just now, you mainly focus on DC motor, which DC permanent magnet motor, which a motor with a PM there permanent magnet. And then you use magnetic field interact with wire, which you learn in the physics, and how we operate on a DC motor. So the one you mentioned just now are DC motor, but actually there's so many different type of motor. If you from the lecture, you can see more than 10, more than 20, maybe more than 100 types of motor. But in this lecture, we're going to show you a few important motors, like the DC motor, brushless motor, induction motor. And then we also tell you about we can operate on DC or AC. What's the difference? How can we operate from DC AC? What kind of definition of DC motor is in a robot, in a vehicle, or in a wind turbine? Which one shall we use? So that's the thing we need to understand about it. And efficiency, I think I asked this question a number of times. What do you think the efficiency of a motor from electrical to mechanical? What do you think? Efficiency? 90%, 50%, 99%, 10%. What do you think?
I'll go with 60%.
60%.
Yeah.
How about the gentleman?
Oh, it's hard to say, because it's like, there's so much area, and I think 75.
75. Okay. Any other comment? Any other recommendations? How about this gentleman? What do you think?
I was thinking about 80, 75.
And of course, the efficiency depends on what type of the motor, what's the power level. For example, some tiny motor for toy, for some little toy vehicle could be really low efficiency, can be about 50-60%. But however, for higher power motor, you have that electric vehicle. You can imagine that electric vehicle on the market, say Tesla. You can't expect it to be 60% because if 40% energy being waste, it's impossible. So the motor inside this vehicle is 95%. That is, it's 95. Most of energy will convert into motion. And it's 95%. You can see that you such a huge of the power losses. The motor only 60%, 40% power losses, then the vehicle will be really hot, just like a burner. Impossible. Right? Even so, that's why all the motor needing at least 95%. Even though really poor industrial joint, 90% will be quite reasonable. Many motor we use in industries or assembly, something like that is 90%. That's something about the efficiency. Example, we mentioned an example, how we use the electrical machine like generator, motor, the factory assembly line, and like electric vehicle, electric boat, many of them, anything moving, robot will be application. So that's why I can see that machine account for such a big enterprise in any building. You see in any one building, all the appliance here, which one will be highest energy consumption? Not the lighting. Lighting like this only consumes about 10% of the whole building. It's in many building, I would say about the AC. That's like AC. Yeah. Air conditioning account for the huge power, more than 60%, which was AC. Compressor is a motor. So that's why motion control is a huge energy consumption system. So that's why I understand more about motor. You can improve the efficiency by 1%, 5%, 10%. You got a big improvement in the total power system. That's why it's so important. Up to this point, any question? So the content of this, today we try to cover this number of topics, including some introduction, and then we talk about inductor first. Inductor is a basic component for motor or for transformer. Have you learned anything about inductor in the circuit? Tell me what you have learned about inductor.
Inductor is like a coiled wire, and the current going through the inductor is LDI. That's what I got.
Okay, and then
That's it. That's all.
how about the issue? Do you have learned about the issue for inductor? How to calculate the field for inductor?
Didn't cover that.
We cover that sometime. That's something we do. So we based on that, we can construct a number of applications like transformer, like motor. They are all key components. And then we try to look into the history of the invention and also looking into how to compare the motor with the engine, like IC engine, internal combustion engine, most of the definition then, and application, we also have an overview of all different type of motor. And then we're looking in other scenario like if we do have air gap, later I will show you what air gap is, why we need to care about the air gap. So that's some of the design we need to do, and then that's about what we try to talk about that. And so firstly, we try to look into about basic covering for the whole machine topic. So all the things already in your canvas, so you can actually download them. So it's three major areas we're looking into. Transformer. You see transformer is not motion device, but it's really nice, really important device for the machine. When you talk about electrical machine, so that is to say a machine, if a machine not really rotating, not moving, it's just more look like a transformer. You can see that many of the motor, like induction motor, AC motor, they actually look like a transformer. Like a DC motor, they have a winding, look like a single winding transformer. So that's why you can see that transformer is the first thing we try to study for all the electrical machine lecture. Even though you buy a textbook, you can see the first few chapter is transformer. Because transformer really look like a machine. We first need to understand how a motor look like, how the winding, the resistance, the inductance look like, and then the circuit will really look like a transformer. So you can see that basically a transformer, I think you all know the operation. We convert electrical voltage from one level to another level. We can able to usually control the current, step up or step down the current. We can also use it to convert the voltage current, but the power usually will be same. Input output may be different by some efficiency, and then but we cannot change the frequency. That's a basic static transformer. But in the future, we learn something more advanced. We can able to change the frequency from some power to transformer. But let's believe me, at the moment, all the transformer only constant frequency operation between input and output. And of course, motor is the major item we study in this course about more different type of motor. So that may include how we understand about linear motor, rotation motor. Mean rotational and linear really similar. We just how we make the stator and rotor. And then we also basically divide them into AC motor and DC motor. So later on, we explain to you what's the difference between them, and then you know how to control and operate them. And then we also have other type of special motor, like the switch leverage motor, stepper motor. Maybe some of you, when you do the project, you have been using the stepper motor. With the common motor, you can control it step by step to move forward and backward. That's really simple to operate. And having said that, and then if the reverse operation for motor, that will become our generator. The generator that we reversely convert from mechanical into electrical energy. And so all the DC motor, you can reverse them become DC generator or maybe AC generator. That's how we operate on the wind turbine or many other gas-fired generator based on this principle. So that's how basically about the topic, the major topic we're going to cover. So in here, then you can see that, and basically a transformer, right? This is the picture that shows you a common transformer. We convert from one level to another level. So we have voltage transformer and current transformer. Basically, we try to convert the voltage or convert the current. So I think you know all of these, we have the operation. Another application will be the isolation, magnetic isolation. We call it galvanic isolation. Then we try to isolate between the electrical connection for safety application. That means wire, they electrically connected, but transformer, the input output are isolated by magnetic barrier. So that means physically, the electrical current can directly, DC current can directly go to the secondary side, that using the same copper cannot. Between that with magnetic couple. So that means in a way we can produce some kind of the magneticity. So I can go for them more. So motor, of course, in here we got a number of different application topics in the motor, like rotational, linear, And then we look into the industrial drive. Then how we use power electronics to control motor, how the transistor look like, how the circuit look like, how to operate on the motor. That's the circuit we tend to use. We also go through some application, like how to use the motor in vehicle, robot, and also generator. So that's a typical application for electrical machine. Then you can see that some motor, you can naturally connect with power source, then the motor can operate, like the DC motor. You can see that why the DC motor has been used for the last 50, 100 years, because it naturally can just pure DC, apply for DC motor, then you can operate. So that's how we see why still many people like to use DC motor, simple DC to operate, simple DC source, we are therefore to do that. And then another important motor is called induction motor. Induction motor is AC motor, basically. If you connect AC source, you can naturally operate. You don't need to control them, pure AC, they can start the rotation. So that means many simple motor, you can use induction motor as well. So that's why for the last many years, induction motor and DC motor account for more than 80% of the whole market. 80% motor, either DC motor or induction. Another 20% maybe some other motor, like the stepper motor, maybe some other switch reluctance motor. So that means if you learn the DC motor and induction motor, you therefore understand most of them. So that's why in this lecture we tend to focus on these two motors so that you can understand how to use them, how the internal configuration. And however, because these two motors can naturally operate by a pure source, but however, if you're using some power electronic control circuit, that means we use some transistor to turn off some voltage and current, we can able to control the applied voltage to the motor, like the applied voltage, applied current, and the frequency of the. For instance, I think we've been using the inverter to join different type of the motor so they can control the speed, like we call variable speed drive, which is common technology we can control speed of the motor. So many today, many of the motor drive, even though some of the EV, we also using USB to control the speed of the motor. So that commonly use electronics to do that. Most of the motor we can use power electronic circuitry to join that to control the motor. So that's common technology nowadays, how we operate a motor. So in this course, we also show you how we're going to use the electronic to control motor. So you know basically how to construct some electronic to operate on the motor. And once we do that, the motor waveform is not naturally assigning or DC voltage. It will become some controlled waveform. Like this control waveform, you do something like chop the waveform, control chopping, chop the voltage, become not pure sine, but chop the sine. Or we use pulse width modulation in the end, which model waveform become a multiple square wave to control the voltage. So that's one of the typical method we control motor. So a motor, of course, we know the basic configuration must be some magnet there, maybe have some magnetic core and also some winding. So the winding internally can construct in very different manner. Besides just pure winding, we may connect a winding in different way to connect them. Maybe I think you know about the star connection, something free winding here. We making a star connection or we make a delta connection. That's for free space motor. That's basically some of the connection. And then we also have some various position with the winding to make the operate properly. And again, we say that transformer also we used to consider as an electrical machine because it's just static, not moving. Basically, if a motor is not moving, more look like a transformer. And the winding, you see, open up a transformer or maybe a motor, you see a number of winding. The number of times can shift, and they're 100, 200, then. So because when we have high number of turns, then we can able to increase the magnetisation or increase the energy source. But having said that, then we tend to make the motor become small if you like to. So if you have too many number of turns, then the motor will be bulky or become expensive. So one thing you can do, we gradually move on to high-speed motor. I think I mentioned to you, the higher the speed, the smaller size of the motor is. I forgot to bring my pen here, but you see that for all the, say, inductance, L equal to half L I square. I think that's the basic equation for all the inductors. I think we all learned that's any storage. But however, then any motor in operate at certain frequency, then you use certain inductance to make up the magnetization. So in the future, if you try to operate a high-speed motor, then what we can do will be, you can see that that's energy storage. Then for the power of the motor, then the power equal to energy multiplied by the frequency. So that means we multiply by the frequency here. So that if we say, if for constant power unchanged, if the motor is 100 watt, 1 kilowatt, that power, if you're able to increase the operation frequency, then for the same time current, the inductance can increase. You can have smaller, less number of turns, smaller size of inductor. That's to say, if you want to operate a motor, we tend to design high-speed motor. Then the whole motor can become much smaller size. Then in the future, you want to operate on a robot, then you cannot afford to build a huge big motor. Then you can put down a high-speed motor. Then in this case, the motor becomes small, it's much smaller size. The whole robot can be much lighter, even the electric vehicle as well. We like to have a high speed, high power units, but if the motor too big, it's nonsense. However, we operate on high speed motors, and the size can be big. For instance, you can see that this inductance control this physical size. So if a motor operates at 50 Hertz, like the 60 Hertz, we operate on a power line in 60 Hertz, then we have this kind of power. But if we increase the motor not from 60 Hertz, 6 kilohertz, then 100 times, then the inductance can be increased by 100 times. Then that's how we reduce the size for the motor. So that's why in the future, we need to think about how to operate a motor to have much smaller size. But in this case, we did a much better operation in the control system, how to control them high speed. Low speed control is quite straightforward. But high speed control, we have to use high speed power electronic to do that. So that's how we're going to do in the future. Yes.
Just curious, are we gonna get into like designing, well, not design, but like into the design of motors that have to very high torque?
Yes, of course. Yeah, we're going to show you about the motor design, how to control the torque. So that means torque control is one of the area we tend to operate on motor. So torque and speed control will be basically how to control motor. Good question. So for instance, I think for motor, we have been using on electric vehicle. Like in here, you can see a schematic for electric vehicle. Then the key component in electrical motor will operate in the wheel. And then motor here, because we want to control the motor drive, we use the driver to control motor to tell the motor what the operation is, like the torque, how much torque we can use, how much speed we need to control that. How do we do that? A motor is set only winding. It doesn't understand anything. So we have to use a motor controller to control the motor, tell the motor what kind of voltage current applied to the motor. So that's how we do the motor. So that's how we can see that on a typical example, how we control motor. So to start how to understand it, then first we need some quick revision for inductor. So an inductor must be a basic component for all the motor and transformer because everything should have some winding. So firstly, inductor. Any and tell me again what is the meaning? What is an inductor? Called winding. You gain some magnetic field and store the energy in there, and then you've got some basic equation, and you do some basic equation for that. Later on, you also need to understand about what the first level, how we calculate the inductor. And basically, inductor we finally divide into air core. That means we don't need magnetic core. We only have winding. That's the air core. And then you also put them on the magnetic core, like the transformer and motor. We usually have a magnetic core. And then, of course, when the number of turns increase, we know the inductance will also increase because most of the inductor is proportional to n squared. So that means if you increase number of the turn, the inductor can increase in a square manner, much higher. Another item we need to look into is the permeability of the core. The magnetic core has the so-called mu R is the relative permeability. Have you learned anything about the permeability? The mu for this magnetic core. So for atmosphere, the mu R equals 1. For many magnetic core, the mu R can be 1,000, 2,000, 3,000, and even higher. Because we need the mu R to confine the magnetic field inside the magnetic core to focus them. So that's how we can do it. So that's how you see the typical permeability, the relative permeability can vary from 1, that means pure air, for 10,000, 1,000, and of the possibility. So, the inductance usually measured by unit Henry. The Henry is relatively large number. For many inductors, we don't like Henry that big number, usually millihenry or microhenry. Of course, for motor, small motor usually a few millihenry, larger motor to 100 millihenry. A huge motor is go up to a few Henry. But usually for many motor, millihenry NH will be more reasonable. And then for really high frequency motor, we may tend to 1 millihenry, so quite small, maybe micro. For inductor as well, for inductor, the many inductor being used for circuitry, we don't usually have Henry, use millihenry or microhenry. So that's the number we are talking about. The basic configuration, you can see that we do have some two basic configuration. Air is just purely air, but in this case, because the inductance is smaller, we use to put them on high frequency operation, high frequency motion control. And then for using ferromagnetic, like the iron ferrite, then we usually can try to increase the inductance. In this case, we use it for lower frequency operation. Lower frequency means 60 Hz, this kind of operation. But the copper wire, we use using insulated wire so that the turn is the turn there will be a short circuit. Then when you observe on a motor or transformer, you can see many winding. But each winding has an enamel coating, so they don't have any contact, physical contact. Maybe you see, when you see the wire, you may not be able to distinguish, but actually there's a coating. That coating will be important because the coating not only behind isolation, they also have a temperature coefficient. If the motor or transformer operate at too high temperature, then there may be breakdown between the coating, then becomes some winding burden or short circuit. So that means a motor or transformer, we tend to operate too high temperatures or too high voltage, it may damage the winding. That's why we try to control motor to be between 60 degrees C or maximum between 80 degrees C. So that we won't burn the winding. So we do have a number of basic formulation like EF, the IDT is the basic equation, and also another basic equation about energy content half L squared. So we all accept basic equation of all that about that. So that's the basic equation. And then another term, I think we also like to understand more about the reluctance. I think you all learn about reduction, right? And anybody can tell me again what reduction is? Have you learned that? Have you learned the term reduction? No? Yes. 65 or circuits reluctant or
I think in the context of circuit theory, it was just like the inverse of the oh god, inductance.
okay.
But I mean, it was kind of like I don't know. I couldn't find a way to like visualize it in yeah, find like a good way to visualize what it means.
Okay. Yeah, something sort of reluctant is something similar to resistant, but in terms of inductor capacitor, we do have some kind of opposition term that we call it reluctant. We do have some formulation to that later we learn them more properly about what they are. No?
Is this different than impedance?
Yes. Impedance is also a kind of the opposition. I mean, the right resistance. Pure resistance, we have resistance. And then for inductors and capacitor, we do have impedance. And then the magnetic circuit, we tend to call it inductance. Just very simple. They all something from opposition terms. Will produce resistance to the incoming current or flux. That kind of terminology. So we do a formulation to look into what kind of reluctance. It's the symbol for reluctance will be something look like we just have some double line in here, it's called reluctance. So the reluctance is something like one of formula here, and which is related to n square and also universally proportional to the reluctance in this kind of formulation. Later on, we will show more detail about that. Then for our basic winding here in the winding, of course, the first formula we learn will be equal to mu H. I think that's a really basic formula we learned, right? Everybody know about this formula. The mu actually consists of two components. One is the mu naught, is the natural permeability, and I think the number is 4 pi 10 to the power 7, -7. And you know that. And then mu r is also the relative permeability. So our without any magnetic core area will be 1. With a magnetic core, depending on the metal material, can be 10, 20, 100, 1,000, and then the flux therefore, the flux transfer magnetic core, then we have this formulation. Then mu ni is more look like the input plane flux linkage, we call them, for apply to the band, and then per unit of the link. For instance, we apply some current into winding, and then magnetic flux will go through this loop, right? The loop link we call it L. So in this case, then we can see that the flux will more look like in this equation. So this is the input can more look like equal power NR current, the input. Number of turn, we produce more number of turn to increase the linking to the conductor. And then the pass through are L in here. So that is the how much path go through. The more look like opposition term, some kind of resistance. Or and then so we give us the first linear. For this one, divided by these two terms. So these two terms we call the reluctant part opposition term angle. Yes.
The mu of the equation does that represent micro, or does that represent I believe in physics there was like a magnetic dipole moment?
We don't go through that one. The mu is called the permeability. Then permeability is how the negativity flow in our atmosphere. So that's why you can see that the mu will be this have a two components. Combined together we call it permeability. But actually we try to relate them to the natural permeability, which mu naught 4 pi 10 to the -7. If iron core can be 5,000. So depend on which material you have to use.
So is mu a constant, or is it also a variable?
Now mu naught is a fixed particle, never change. Mu r relative permeability depend on your material. For fixed material, you should be fixed. You may vary slightly depending on temperature or other environment. For example, for instance, you got any iron here, and maybe this aluminum, you got a fixed metal out for this one. Over the metal out for aluminum really small, we run by something because they are not real material. But for iron, then the iron only a few hundred, a few thousand. So you can check the data book, check other data, you can see what durability they are using. For instance, in the lab, I will ask you to make a transformer. In this case, you need to measure the mean for a transformer. To with a measurement contact measurement, to check what's the permeability for the magnetic core. Even though you check the data book, and if you want to buy a component by magnetic core, then you can ask for what is the parameter for real the relative permeability. So that's the parameter you can get from the manufacturer. So another term is called MMF. MMF metromorphic force. Anybody heard about this term? MMF, right? MMF is more look like the input voltage. Of course, in circuitry, electrical circuit, we call them electrical voltage. For magnetic circuit, we have a term called MMF, more look like the input voltage, but they're not voltage, they're magnetic voltage. So, so this thing is mainly controlled by the ampere term. Ampere term means I is the current, input current. N is number of turns. So you can see that when you put one winding, the energy input, the magnetic input only one winding, for the current find. But in two terms, we more look like we're putting two 5N into the circuitry. So that means the excitation of higher input energy. So that's why we call it this MMF. If you want to increase the input capability to a winding, you tend to increase the MMF. Right. So MMF by definition is that number of turns times the current through N times sine. So the basic definition for the terminology we call NMF. So MMF is an open concept. If you learn about the circuitry, it seems you haven't learned about MMF yet. Right? So MMF later will show you more example. In the first lecture, I just give a few equations to you, check with you how much you understand, and then adjust the later on action, and then work they are. And then you can also provide some material to you so that you understand more about it. So MMF is sometimes a symbol called MMF or F the force, input force, or input more magnetic voltage to the system. So MMF should also have another formulation H. H is another magnetic intensity. So that's another terminology. Have you learned about B? That one term you learn, and H field, B and H. I think you have learned that, right? Yeah. So for magnetic, that H is another magnetic terminology we learn. Then the magnetic H, then multiplied by the length of childhood for magnetic flux, and happen to equal to the magnetic multiple for MMF. So that's how the basic magnetic equation come from here. Later on, we will have some more equation to show you application, how you operate on the magnetic equation.
Wait, when you refer to the B and the H field right now, is B still like magnetic field and H still magnetic field density?
B and H are slightly different. The B is the magnetic field density.
Okay.
More look like per unit area. If for large area, same kind of magnetic flux, we got less B field. So the flux look like the current. The flux is the same anyway. When the flux pass for a larger area, we got less become less B field. But H are more look like the magnetic flux, mainly related to the permeability. Okay. Yeah. So that's why you learned before. We got a pH group here. It's a really famous pH group. So when you input here, more like the current multiplied number of turns, right? The input pH field And then when you increase the input current, the inductor gets more magnetization, the P field inside will start to go up. Somehow it will go to a saturation, maybe here. Initially are more linear, but gradually more fractal, it's a saturation. Why is saturated? Because the internal some of the dipole will become the moving projectile. It's not the active band, accumulate more of the magnetic magnetization inside it. So the mu is this ratio, the convergence. You can see that the slope here more the mu. So that means the initial mu is like that, but the initial more like saturation, the mu will become more flat, much lower. For instance, magnetic core maybe have 1,000, but when we increase the current, the inductor, then the getting to the saturation, the mu out of the breathing will getting lower and lower. So that means the performance for inductor, you're getting less. So for instance, the transformer, we really work about saturation for transformer. Have you heard about the transformer saturation? You know, transformer, we tend to use AC applied to the transformer, we don't use DC. Have you heard about that? And because AC, we can customize it, we can find the magnetic field, we won't use it as saturation. But then DC is always the same magnetization, then the type will get saturated eventually. So that means for transformer, we don't use DC to do that. So that's another scenario we will learn it in the field. But if you do study the electromagnetic, then you can understand more about it. So of course, I'm just here, I give you some basic equation. But when we operate on DC motor or an industrial motor, we don't have to use all these equations. I just in the first lecture to see how your knowledge in the electromagnetic, how much understand about basic concept for inductor and basic equation for inductor equations. Okay. Any question up to this point? So, in many texts or many literature or websites, we tend to do some comparison between the different kind of the circuitry here. And I think I have to say this side is electrical. Yeah, this side is magnetic comparison. Anyway, from this whole circuitry, I think you learn all these book page is the basic driving electromagnetic force. And then the current, the opposition term is the resistance rho L over A. That's the terminology based on so we learn all this. But when we go to magnetic circuitry, then we have another terminology, which is something terminology. The first thing will be the element called the electromagnetic force, which look like a driving voltage. And this driving voltage, when applied for the winding, so that's how all this winding, we call it electric. And then we therefore create the magnetic flux. The flux look like the current. So that's why you can see these two are really similar to each other. In many cases, when we analyze on magnetic circuitry, we can use this kind of so-called Ohm's law, this kind of circuit operation parallel series to calculate voltage and current. In this case, we can calculate our NF of the reluctance of the flux. So if I have a really complicated magnetic circuitry parallel series, we can calculate the magnetic flux or magnetic flux density for each of the paths. So the basic equation for this kind of reluctance will be like that. So very in a way, there's some similarity to this equation. We also, in the numerator, we got the length for the core. In this term, we got the length for the resistor. We got cross-section area. Cross-section area here. So they do have some similarity. So this table is very famous. If you go to any textbook, go to any website, comparison between magnetic circuit and electrical circuit, will show you this table. So that's how we compare them. So what we need to see that will be for electrical circuitry, we got different voltage, different operation current, and the opposition current resistance.
So all the concepts on the left side are labeled magnetic circuit.
Yeah, just now in the beginning, I say I have typewriter. It's like here. This one is electrical, this one is magnetic. So that's why for magnetic surface electricity here, driving force will be M, we call it. And then we also magnetic flux here, you got the reactive group. And then you got a similar law. Hawkinson's law is actually also. So that's how we understand, how we compare them. So in the future, if we design complicated magnetic circuitry, you can convert all the components into the reactance. Later on, I show you reactance. You can use the basic formula to calculate the reactance, and then convert out the circuitry. The circuitry is exactly the same voltage mode on basic electronic circuit. They're the same anyway. What time is it now? I'm just trying to figure out.
54?
52. So we still have 20 minutes. So the efficiency of machine, as I mentioned before, for transformer is really good. Efficiency usually about 99%. I think I mentioned to many of you, a good transformer usually about 99%. And then, of course, some of them may vary between 97 to 99, depending on the power level. For more than 95 will be quite a common law. Of course, for some really lousy motor, maybe lower, maybe 90, 80, something. And so that's you can see the efficiency for motor and transformer, how it look like. The best operation for motor or transformer is room temperature. They all designed under the room temperature. So however, because of power loss or the efficiency, then the temperature for motor and also transformer may go up. So as I mentioned before, all the magnetic property are not working really well at high temperature. The magnetization may lose, the new out of permeability will drop. So that means if you increase the temperature, then the magnetization will drop. Let's do that the inductance will drop. Inductance will drop because higher magnetic flux will need more saturation. So that's a kind of the avalanche effect. And so temperature is one of the issue. And that's why we tend to operate a motor in a controlled environment. For instance, if you go to an AC room, maybe air conditioning system or data center, they tend to have air conditioning to control all the equipment so that under the lower temperature or the overheated. So that's why operation temperature will be counted. If you don't do anything, you only use natural cooling to the machinable motor, you may end up with overheating. And then what happens will be the winding will have problem, short circuit for the winding, aging, the magnetic core may lose the magnetization eventually. For those PM permanent magnet, then you know that once they're permanent, then they overheat them, then they lose the magnetization. I think you learn from the physics, if they have PM, you burn them, the magnetization will lose everything. So that's why temperature control operation is something you need to be careful about. So that's the bullet point for the high temperature operation. So that means we need to, so the magnetization could lose permanently, maybe even temporarily. We don't like that. The copper wire may break down. Why is that? Because the coating are temperature sensitive. So in this case, at high temperature, then the coating may melt or break down. So if you check the copper wire in any data book, they will tell you about temperature operation. Most of this wire is 120 degrees C. So that means you can see that if you measure motor externally 80 degrees C, internally maybe even higher temperature. So 80 degrees C is really, really upper limit. I think I will try to control it 60 degrees C. And if you want to go for high temperature motor, you need to make special unit copper wire that will be more expensive. If you go to any website, then you can see the copper wire at different temperature grade. So the most common one only 120, 130. Really expensive copper wire maybe go up to 180, maybe more than 200. You seldom do that because too expensive. So that's why you can see that we try to offer the motor in this kind of the temperature range. So here with some history, I think you can check it quite easily in many websites. I think, and 7040, I think we started some initial work for electromagnetic principle, which we see that it's not really a motor yet. It's just show you some electromagnetic attraction using this method. Then 1820, we start to using wire to create magnetic field. So that's how initial work we tend to create some magnetization. So that's some of the future. And then the same time, then it's able to create two current wire to create the force between them. So that is the initial thinking, how we're able to create the force by the current carrying wire. So that's the initial work, how we put down the background for motor. And then somebody was started in that microfarad, I think you all know the name, right? So he was first device able to continue magnetic movement. So in 1922, there's a really simple motor, and then we able to have easy continuous doing some continuous rotation. So that's how we develop the initial motor work. So 1835, so we started to have first more promising this motor. We also paid them. So you can check the US paper one. If you can see the number. Now I think the US paper number is so long. It's initial paper 132. The first 132 US papers during that time. And then later on, we got more promising, more commercial. So, and Tesla also developed his own AC motor. The previous design of DC motor, really. So, but Tesla developed the first AC motor using AC current with the first motor. So that's a really, so Tesla is a really famous guy, really promising in the electrical energy history. That's why the vehicle used its name Tesla. And then gradually we move on to how to operate a very kind of DC system and transmission system. And then we in 1988, we started more patent on this work. And one of the large companies, the Western country, really big enterprise for electrical engineering. So they start to develop this kind of AC motor. So we could say the first really practical industrial motor is invented in about 1887. That's what you can see that more than 150 years. So during that time, you can see the oil under this, then we gradually to have electric vehicle being developed during that time. So because we do need the operation for the DC motor and AC motor. So that's to say, EV is not really new. Once we develop the electrical machine, we have the EV electric vehicle. So therefore, we ran many vehicles. You can help the popular about nearly 200 years ago, 180 years ago. Then during that time, coexist between combustion engine and also electrical motor system. Four of them were there. And then during that time, 100 years ago, they have competition. Which one was the winner? They both coexist at that time. And EV during the time was really good because zero emission, easy to make, only copper wire plus some magnetic core, then a little transformer. But the key thing is, in that time, the energy storage. We do have the massive battery in that time. Massive battery was invented more than 200 years. So we do have energy storage. We do have motor. During that time, we make the electric vehicle, but because the battery is not doing a good job during that time, the vehicle can only travel for 10 miles, 20 miles at most. And also take a long time, 10 hours, 20 hours to charge up. So that's why not many people like it. But hey, it seems that during that time, 100 years ago, there's a lot of the activity in EV, also in high-CE vehicle. So here will be one of the first prototypes of the vehicle 1533. So in that time, there's many various type of motor being developed during the time. And then they also made up this one of the first vehicle. You can check the website here to see how it looks like. They also have an exhibition to show the operation. So the development is important of that. It's battery powered. the good thing is, of the low noise, but the steering, they still don't have really good steering system. They don't have differential speed steering, so that means the control is not very good. So that's another really famous electric vehicle during that time, Thomas Parker, even the Wolverhampton 1882. So I think this also really famous picture in many websites. When you check the dimension for the EV, you usually see this picture. So here, engineer working in underground during that time. So that's why you can see that when we tend to compare the motor and engine, so what's the major difference between them? And you know that motor is convert electrical into mechanical energy. Gasoline is using chemical energy. The both of them are working really well, but this mainly on electromagnetic, but this one mainly rely on ICE internal combustion engine. But the major comparison will be firstly the efficiency and the performance. So you can see that the efficiency for Disucks not very good. We know that 15% is quite a lot. Maybe some good 15, some poor one may go down to 12 or so. So really not very good efficiency. And also the emission is unusual and torque profile, the torque control is not very good. The zero speed torque, standstill torque is really poor. So that's why there are two vehicles in the traffic light. One is the emission, one is the ICE. Then once you change the light, then the EV will go first because the initial torque is so huge for electric vehicle for more. And so the torque speed control is difficult and you cannot control torque properly. For EV motor, the efficiency at least 90%. Most of the motor will be 95. So of course this advantage. And also low emission, clean, low noise, speed control, united speed control. Once they have been using EV, you see that the torque control is so good, you can overtake any vehicle without any difficulty. So that's why once you have been using EV, you don't need to use gasoline car anymore. So that's you can see the major difference between the motor control. We can control motor really much easily using electrical control, but for ICE, we can't control the speed really well. So that's why you can see that for the next 10 to 20 years, all the vehicle, that means the motor drive different will be the winner. So another major comparison we had to do with how to compare DC and AC motor. You see DC motor, you can basically, the definition would be you can use DC to control for motor. AC motor, we can use AC to control AC motor. That's the basic definition between them. And then between them, you can see that conventional DC motor, we got the carbon brush and commutator. This connect with the electrical power to the winding. Because when motor rotates, we need to continuously supply the winding. We need to turn the winding at 150-degree phase angle. So that's why we do need a commutator. So during that time, the conventional DC motor do need to use commutator. So that's one of the disadvantages for this motor. And then all these things can sometimes also got aging with the start, which they don't quite like. But however, the speed control is really simple, straightforward. We can simply do this driving voltage, we control the torque and speed really much easy, really simple. So that's why once we use this mode and control them really low cost, really simple circuitry to do with that. But the maintenance is a problem because we do need to take care of the commutator and the carbon brush. So that's something we don't have. But AC motor could be different. AC motor don't have any this kind of commutator and brushing. It's contacts between the stator and the motor. The rotating part have nothing connected to the stator. So that's why much higher reliability and also nighttime will much better. But however, the speed control are more complicated. Later on, you learn from this course. This is major development here. How we make the control, how we control speed, how we control the torque. AC motor governed by frequency. Our power point here is 60 Hertz. So naturally, the mode itself are running 60 Hertz. But if we want to control motor speed from 0 to 60 Hz, then we need there's some control circuitry. So we cut our input frequency all 60 Hz. So that's the technology, how we regulate the input frequency for motor. So that's the job for motor control systems. That is the power electronic control system with input. Because there's a low pressure, so that's why the maintenance will be much lower. So that's the thing we quite like to see that. So application, this kind of brush motor, simple, easy to use. So that's why I've been using them for toys, other hobbies, and small appliance also being used. In old days, then we do use them for some automotive applications. Some really old day EV, we still use them. So, about 30 years ago, and some of the small motor, then like this application, we tend to use this kind of DC motor because they're really cheap and low cost. We tend to use them. And for other industrial drive systems like this, and then we tend to use them. Some other component, we may also use that, but of course, many of them start to use brushless anyway. So these are which one is so tend to do. So, but brushless DC motor and brushless DC motor are quite similar, but just one of them will be more expensive. So in this course, we'll also show you about the brushless and brushless DC motor, all of them. Then you can understand the difference between them. So this kind of the brushless DC motor, and very similar to the conventional DC motor, but they use another configuration to develop the contact point for the winding. So because of this low physical contact between the rotor to other part, so that's why many high performance are done by them. So even though some EV application for some fine vehicle robot, we tend to use DC brushless motor. So this is a really famous motor nowadays. Nowadays we got a lot of the application. We tend to become all the conventional motor, DC motor, that we gradually move on to use this brushless DC. So AC motor is also conventional motor. 40% of the market share, at least using this kind of industrial motor. So many of the industrial drive, including the compressor, the fans, pump system, are using industrial motor. Many AC pump, which you have seen, or AC drive fans are using this. Many home appliances, like the washing machine, dishwasher, any moving part, and most of them will be using this AC motor, industrial motor. Water pump AC system, and large industrial plants and joint are using this. So at least 40%, some of them may be even higher. We go up to 50, 60% for the market share. But having said, you can see that back to 100 years ago, in that time, this is one of the pictures they took in New York City. In that time, we got 1/3 of vehicle on electric. 2/3 are gasoline. So surprisingly, in that time, 100 years ago, we got a good portion of electric vehicles are using more electric motor. So that's why, but of course, after 1912, we got really good development for ICE. So that's why ICE perform much better than motor during that time. So that's why from that time onward, they've been using 60 years of the gasoline vehicle, but now come back to electric. So here will be one of the first development of this vehicle by Henry Ford. He developed his own company for automotive, become really famous during that time. But many other vehicles, even the lunar vehicle are electric vehicle. Like here, the first lunar vehicle in the moon. Even the Apollo program 15, 16, 17, they also send the electric vehicle to the moon. So the power level not very high. The payload 490, the speed really low, 13 km per hour. The motor really small power, 0.19, really small. The battery they still using less battery than the time. You can see that. So EV has been here for many years anyway. So here a quick revision for the historical development for EV. You can see how in the last many years While we come to in 1912, we got a very big development of EV in the whole market, mainly because of this development. A lot of the electric motor, electric power battery system being designed for EV. We think EV would be a good market at that time, but eventually we being overtaken by the IC engines. Since we have a really good IC development. Finally, there's another good picture to show you all the motor being available. You can see there's so many motors being available. We got the commutator base and also without any commutator. And so like the conventional DC motor or this type. And then we got we're going to focus on nested motor, but we do a different type of motor, which we may not go through that important. And then you can see this motor, we got two major types, one and cage motor. And then more importantly, you can see the brushless DC motor, also important brushless DC motor. And then commercial motor, low cost motor also in here. So we got a whole picture here. We don't have time to learn all of them. We only see a few important major market share to show you how to operate. But this one will show you all the various types of motor in the market. Okay. I think we'll also spend some time how to design motor. One of them will be the air gap motor. Could you tell me about the time now? What time is it now? Oh, 15. 13. Okay, I think we're going to cover it next week. But before we go away, then I just tell you about the arrangement now. And one thing about the course configuration will be, I firstly introduce to you our TA. Maybe Xiaodong, you can set up this our TA for the course. Anything you're not quite sure in the company. And tomorrow we're going to be on every Thursday we're going to have but not tomorrow and set anything there. But start from the week after, we're going to have the lecture. So Xiaodong should help us talk about that. So all the marketing will be on the team or will be any question. And for me, then you can see our syllabus. Maybe quickly to go through our syllabus before we go away. Oh, this one. Yeah. Basically, I think I also upload my tentative syllabus in here. You can see briefly about what we're doing. So all this about PLO, I think you know that. We do have some textbook or reference book. They're really expensive, a few $100. I don't think you should buy it. Yeah, but if you like, you can. But all my lecture material will be in my notes. You don't need to refer them. So only my notes will be good enough. But if you want the deeper knowledge, you can also procure a few of them. And so in here, the arrangement for the grading will be like that. We have homework, quizzes, midterm exam, final exam, also lab. The lab will be every Thursday, as I mentioned. Then, as usual, that's roughly about the teaching schedule. You can see here. So we do have homework for every 2 to 3 weeks. We have the homework assignment. In here, we have midterm in here, roughly week number 7. And then we also have quiz 1 and quiz 2 here. Totally 5 homework. So that's initial arrangement. So during that, I will post the assignment to all of you. So that's roughly about the schedule. Next thing I'd like to discuss with you will be the lab arrangement. Quickly. So we're going to organize about 4 to 6 labs. And then initial lab setup will be looked at 1 to 6 labs, depending how much we set up. So we have 2 transformer that one would be how to measure parameter, and another one how to construct with your own transformer. And then you have DC motor to test a DC motor, do basic measurement for DC motor. And then you also construct, so you have to design, construct our own DC motor. And then you also have industrial motor testing and also personal DC motor. We total the work at 6 steps, but given our time, because the first time we all organize it, so we change to set 6 steps. Because we roughly have 24 students here, so we have around 3 students in the group. Then I will try to prepare a Google Share file. You sign in to form group of 3 students in the group. Maybe some, maybe 2, maybe 3. Mostly will be 3. It depends on 24 divided by 3 will be equal to 10. So, and so that means each lecturer was able to take care of half of the class. So you will come every 2 weeks. So in order to do it. So first day you don't need to come every week or every 2 weeks. So for the labs, each time they include construction, make up some prototyping, conduct measurement, record the data, analyze. So that briefly about what we tend to do anyway. So we do need to have a lab report. You totally have 4 to 6 labs. And then you don't need to do all 6 reports, you only select 2 you think the best. So that means your report should have all this content, if you all know this, introduction, basically, and then of course with the same group, you should have similar waveform, photo, data here. But your analysis conclusion could be different. So then each one has to submit your own report. So the rough time to submit, we have only 2 reports to submit. So after the following number 8 and 15 will submit these 2 reports. So with 8, you should have probably done about maybe 2 to 3 labs. Then you can select the best one to submit one, and then for 15 submit another one. So that's the way to do it. So we tentatively to set the time schedule will be something like this. So start from next week, then this time you are coming to 12 students half class. So you come here, week 2, you come in alternatively like this. On that order. And then for first few class, we set the transformer testing. Because transformer is the first teaching material we have. So we first work on the transformer, and then later on we work on the DC motor. This motor, we got 2 sections. One will be some measurement, and another will construct our own DC motor. And then also industrial motor, bus motor. So that's how we do the arrangement. What with the user time schedule like that. Later on, upload Google Share file. We tend to form around 3 students in your group, fill in the timetable. So that's how we're going to organize the next section. Any questions? I also post our TA contacts in the canvas. There any questions then also consult with him. And then so that's it. Any other question, comment, anything? Yes.
So like, how do we decide who's going to will that be decided on the two list?
That's right. I will design all the left book in my timetable. That will be the way you can use the motion to put the motion. That's it. Okay, see you again next meeting. I think next Monday we have no class before holiday, right? Yeah. So come back on Wednesday. So see you then. Bye bye.
Hey, what do you think is the best kind of like I like working with the electronic stuff by hand. So what do you think is the best like interactive way to learn in this class? Taking apart motors.
My lecture will cover all the theory and practical stuff. But the hand-on thing will be on Thursday, the lab. The lab will show you practically how you conduct the measurement, how to create your own transformer and motor. You do it, make your own motor, can construct motor, construct transformer, hand-on. So both of them are really important. You just follow my course, you can learn all the theory and hand-on experience. Excellent course. Yeah.
I just want to introduce myself. I'm really excited to take this class. I was a little tired today, but because it's the first day of school, but no, I'm excited for the subject. I really want to learn about like electric vehicles and all that.
Yeah.
And I'm also interested in self-driving cars. The AI towards it. So having both sides is really interesting. But yeah, I just want to say I'm excited for the class.
Excellent. Right. And this semester I have this motor. I think next semester, I think there will be power electronic, I think.
Mhm.
And then the semester after will be electric vehicle. I don't remember the sequence,
Mhm.
but so they are all really important courses
Uh-huh.
for all the future technology.
For sure. Thank you.
Okay, great.
Nice to
Great
meet you,
to see
Professor.
you. Okay. What do you think? It's good.
Yeah, I think it's good. But is there a way that I can access the syllabus since I'm
Oh,
still
I already posted on the camera.
Yeah,
And I tell you what, you email empty email to me, I can reply to you all the material and the link. Because at the moment you cannot arrange that, then I can send you the material by email.
Okay.
You send me an empty email.
Okay. Thank you.
Good. Hi. What do you think?
Chang, I haven't gotten the email yet, but I realized that I need to talk to my counselor as well to get
Okay.
approval. So
I already endorse it. So I
Yeah.
think now the system goes to next level. I don't know how they approve it. Yeah.
I'll talk to my counselor. I'll
Okay.
deal with it now. But I really
Good.
do want to be in this class. Very
Right.
interesting.
Right. Excellent. So what do you think? Any comment?
Any comment on this? This is a lot of information. It makes me very excited for the class.
I
But
agree.
I have some questions. Last semester, you recommended working on the e-bike for IEEE, and we're trying to find another competition to become a part of. Do you have any ideas or hints on where we should look or competitions you think that would be good for the club?
Right. Actually, in IEEE, I saw your submission already.
Yeah.
And the system already doing their own grading.
Mhm.
So which other competition are you thinking about that?
So Brandon proposed we do micro mouse. So that's one that we're looking at, and we're not too sure about any other competitions to compete in. We know there's a micro mouse competition. We haven't found an exact one yet. So I'd like to know if you knew any, so that when I have
I
a board
didn't
meeting.
check anything yet, but tell me more about the micro mouse. What is that?
I believe micro mouse, from what I've been described, is it's a little like RC car, and it autonomously makes its way around a maze as fast as
I see.
possible.
That's the
Yeah.
thing I saw the other day in your in Asher's yeah. Okay, that is also quite interesting.
Yeah.
But so maybe anytime you can grab me, I can have some discussion to see how we're able to win the competition. I mean, so we need to go for all possible competition. So there's as many as possible.
As many as possible? Okay, so maybe we'll
because
do
one
micro mouse and something
of your
else.
design, you can able to enter a few competition. Let's try to optimize our participation. Yeah.
Okay, but you don't know exactly where to
I
look
look
to know these competitions.
There is a major competition on e-formula vehicle. But e-formula vehicle is quite a big investment because you really need to design the whole vehicle quite a lot of time. But however, you may start to do it now, you may take at least 1 year to prepare for it. So the e-formula vehicle, there's are many global competition, like the most famous one will be in Australia. However, there's quite a few also in different part of Asia or Europe. So I checked my friend to see which one will be more recent one. Then you may start to prepare for it. I think e-formula are one of the major one, big one. You should go for it. Yeah. At least.
One thing that I'm concerned about the EV is isn't that I believe we have a Bobcat EV team already. So I'd be concerned that I'd be like kind of stepping into that club's activities.
So tell me more about the Bobcat EV team. What are they doing? What project, what kind of competition are they go for?
I don't quite know. I just know that they make a car and it's an electric car.
Okay.
I don't know exactly
How big the
about it.
car is for how many people? Is for competition or for golf car or formula?
That's a lot of like factors. So maybe we could try to do two different type of EV competitions. Okay, so
that means that team belong to the ME department or what they who are they? What kind of the group or which department, which faculty are they from? Mainly.
I think they are mechanical. I just know they're one of the other like clubs. I don't socialize much with them. But I can try to find out more, and then if they are, I can find out what competitions they are so that we're not like intersecting. So that would be one thing we could do. We could do a Europe setup and maybe do what competitions like that. Okay.
I think actually, if you want to develop our own Formula E, it may take quite some time.
Okay.
Probably it's not just a few months. Probably it take at least 1 year. So if to prepare now, probably by the coming summer, you can have something. Then we check about the time we need to enter the competition. I will check them. Okay, then
Okay.
maybe you can also check about various competition. So there should be quite a few.
Okay, thank you. I'll come back with any other ideas for
Yeah,
projects.
great.
that get
Thank you.
approval.
Yeah,
Thank you.
Okay, thank you.